Removal of overburden involves excavating soil and debris above the bridge structure to prepare for the lifting and stabilization process. Drilling micropiles involves creating small-diameter, deep foundation elements to provide additional support beneath the bridge. Freyssinet bar is then installed to enhance stability and distribute load during the lifting operation. Filling removed behind the abutment involves reinstating excavated earth or material to ensure proper support and stabilization of the bridge during and after the lifting process. Core drilling into the abutments creates precise openings for the jacking systems. Forming bearing slots allows for the optimal positioning of the bridge's new elevation, ensuring secure load distribution during lifting. The wire saw cutting process employs a high-tensile wire equipped with diamond segments to precisely slice through masonry. This method initiates after drilling, allowing for controlled cutting of the bridge's arch, facilitating its elevation while minimizing damage to surrounding materials. Hydraulic jacks are strategically positioned to initiate the lifting. The jacking process begins, lifting the bridge gradually upward. The hydraulic jack control deck manages the lifting operation, synchronizing the jacks to ensure uniform elevation and stability throughout the process. Synchronizing the lifting sequence ensures all hydraulic jacks operate simultaneously, maintaining balance and preventing structural stress during the bridge lifting process. The structure is successfully raised to a height of plus 900 millimeters, marking a significant achievement in the lifting process. This elevation facilitates necessary modifications for the railway underneath, including infrastructure upgrades like electrification. The lift is an essential step in ensuring the bridge meets modern standards while preserving its historical integrity. Accurate positioning is maintained throughout the process to ensure optimal stability and safety. After reaching the initial height, the structure is carefully lowered to a final position of plus 450 millimeters. This controlled descent ensures precise alignment with the newly formed bearing slots, allowing secure integration with existing supports while maintaining structural integrity throughout the adjustment. In Phase 1, embankment excavation, the project team systematically dismantled the king post wall, creating necessary clearance for the bridge slide. They then installed a temporary nosing to provide structural support. Bentonite clay was applied as a sliding medium, facilitating smooth movement and reducing friction for the subsequent phases of the operation. The removal of the king post wall involved a methodical disassembly process, ensuring structural safety and minimizing disruption. Heavy machinery was utilized to carefully take down the wall, allowing for controlled removal of materials. This step was crucial in creating the required space for the sliding operation of the bridge beneath the railway line. The installation of temporary nosing involved constructing a robust support structure to ensure stability during the bridge sliding operation. Engineers carefully aligned the nosing with the existing bridge framework, utilizing steel plates and fasteners to secure it. This temporary structure was essential for safely managing weight distribution and preventing any movement displacement during the slide. Bentonite, a fine, absorbent clay, was selected as the sliding medium for its ideal properties in facilitating movement. When applied between the bridge structure and its foundation, it formed a slippery layer, significantly reducing friction during the sliding process. This allowed for controlled, gradual movement of the bridge at an average speed of 3 meters per hour. The use of bentonite minimized wear and tear on the infrastructure and provided a smooth surface that enhanced the efficiency and safety of the entire operation. Excavation Phase 2 involved targeted digging around the structure to create a clear pathway for the controlled sliding of the bridge. The hydraulic jack control room was established to monitor and manage the hydraulic systems, ensuring precise control during the bridge sliding operation. During the sliding process, the structure was controlled to move at an average speed of 3 meters per hour, which was crucial for ensuring both safety and precision. This controlled pace allowed the engineering team to closely monitor the movement, adjusting hydraulic jacks as necessary to maintain stability and alignment. The slow rate of movement minimized the risk of structural damage or misalignment, enabling real-time assessments and interventions if needed. Engineers conducted continuous inspections as the bridge slid, ensuring that the bentonite sliding medium adequately reduced friction. This meticulous approach not only facilitated a smooth transition but also adhered to strict safety protocols throughout the operational phase. Once the bridge had successfully slid into its new position, the next step involved reinstating the earthworks and backfilling the excavation sites. This process required careful layering of soil and materials to recreate the original embankment profile, ensuring stability and proper drainage. Specialized equipment was used to compact the backfill, preventing future settling and erosion. Additionally, measures were taken to restore the surrounding landscape while also accommodating any necessary utility adjustments. This phase was crucial for ensuring long-term structural integrity and to facilitate safe access over the newly positioned bridge. Upon completion of the earthworks, the site was thoroughly inspected to ensure it met engineering standards. Subsequently, railway tracks were carefully reinstated, aligned, and secured, restoring operational functionality and enabling safe transit for trains on the Immingham to Ulceby line. Over the weekend of April 5 to 7, 2024, a significant engineering feat took place on the A1 motorway in Richterswil, Switzerland, where the mobile construction bridge known as the ASTRA Bridge was erected. This advanced structure was set up on the direction towards Zurich, marking a crucial step in maintaining the flow of traffic, while extensive construction activity was executed. The operation began with the arrival of 47 heavy transports, which carried the various components necessary for the bridge assembly. Each vehicle played a vital role in delivering the materials to the site, showcasing the logistics prowess involved in such a large-scale project. Transporting heavy and oversized components demands precise coordination, especially when maneuvering on busy roadways. Upon arrival, the first phase of construction involved the delivery of the upper ramp. This critical component is essential for providing proper access for vehicles traveling on and off the bridge. The assembly team swiftly commenced the installation of the upper ramp, ensuring that the structure would be stable and capable of supporting traffic as efficiently as possible. Working under the constraints of limited time, the team prioritized safety and precision throughout the ramp's installation process. Simultaneously, the assembly of the lower ramp commenced. This part of the bridge, while equally important, posed its own set of challenges, especially considering the necessity of alignment with the upper ramp to facilitate seamless transitions for vehicles. The team successfully integrated a new rounding element designed to enhance the structural integrity and aesthetic of the bridge. This innovative addition demonstrated the forward-thinking approach of the engineers and construction teams, who continuously seek to improve upon traditional designs. As the first night of assembly drew to a close, work began on preparing for the second night of operations. This required planning, as the successful execution of subsequent steps depended on the smooth orchestration of events from the previous night. A schedule was laid out detailing the tasks that needed to be accomplished, including the delivery of the bridge portals, which would not only enhance the bridge's structural stability, but also support the overall design and functionality. During the second night, the delivery of the bridge portals commenced, marking a pivotal moment in the assembly process. These large structural elements were carefully positioned, with their locations meticulously calculated to ensure optimal load distribution across the bridge. Following their positioning, the installation of intermediate elements began. These elements served to integrate the bridge portals cohesively, reinforcing the overall structure and enabling it to withstand the stresses imposed by heavy traffic. An essential task included connecting the data lines, which facilitated communication between various systems within the bridge. This integration is crucial for monitoring structural health and ensuring the safety of all vehicles traveling across the bridge. A total of 18 bridge portals were strategically incorporated into the design, each contributing to the stability and functionality of the structure. As the assembly progressed, the team prepared to connect the bridge halves, a momentous step in the construction process. With precision and coordination, the halves were joined together, solidifying the bridge's integrity. The culmination of this endeavor over just 2 nights speaks volumes about the skill and efficiency of the engineering and construction teams involved. By the end of the weekend, the ASTRA Bridge had been successfully erected, ready to serve traffic while seamlessly facilitating ongoing road improvements in the area. The scenic route from Interlaken Oost to Briens, renowned for its picturesque landscapes and breathtaking views of the Brienzersee, is undergoing a significant transformation. The RGEE Brienzersee has embarked on an ambitious project to replace over 2 kilometers of roadway under total closure conditions. This challenging endeavor is focused specifically on the Seng and Chubom tunnels, which span 860 meters and 1,355 meters respectively. The project marks a significant step in improving the infrastructure of this beautiful area, ensuring both safety and enhanced travel experience for the thousands of visitors and locals who traverse this route. The primary objective of the road replacement project N08 is to enhance the structural integrity and safety of the roadway that serves as a vital connection between Interlaken and Briens. Over time, natural wear and environmental factors can take a toll on road surfaces, necessitating periodic upgrades. This project is particularly important given the popularity of this route among tourists and residents alike, who rely on it for daily commutes, recreational travel, and tourism activities in the stunning Bernese Oberland. Preparation for a project of this scale is no small feat. The ARG Brienzersee team had to meticulously plan every detail, from logistics to the timing of the road closure. With a strict timeline of just 48 hours for the entire operation, every moment counted. To ensure minimal disruption to traffic and to complete the work efficiently, the planning phase involved collaboration with local authorities, traffic management systems, and community stakeholders to inform the public and provide alternative routes. As the road was closed to traffic, the ARG Brienzersee crew moved swiftly to begin the replacement process. Using advanced machinery and skilled labor, workers removed old asphalt and repaired the underlying infrastructure before laying down new, durable materials designed to withstand heavy traffic and harsh weather conditions. The duration of the road closure was not merely a logistical challenge, it was also a test of the team's coordination and efficiency. Safety was a top priority throughout the operation. The project site was clearly marked, with detour signs in place to guide drivers around alternative routes and ensure pedestrian safety. The strategic planning allowed for smooth transitions and minimized risks, creating an environment conducive to focused work. While any road closure can pose inconveniences, the long-term benefits of such projects are invaluable. The successful completion of the road replacement in the Seng and Chubom tunnels will result in improved driving conditions, reduced maintenance needs in the future, and ultimately, a safer transit experience for everyone. Local businesses can also expect to reap the rewards of this infrastructure upgrade. A well-maintained road encourages more tourists to explore the area, which can significantly boost local economies reliant on tourism. For residents, enhanced road surfaces can mean less wear and tear on vehicles and reduced travel times. The recent installation of the first BEBO arch in Sarawak, Malaysia, marks a significant milestone in modern engineering and infrastructure development within the region. The BEBO arch system, renowned for its unique design and structural benefits, has been successfully implemented to enhance the functionality and durability of local infrastructure, particularly in bridges and culverts. The video documenting this landmark event provides an in-depth look at the entire process, from the design and fabrication of the BEBO arch elements to their transportation and final installation. Each step is captured, showcasing the advanced technology and craftsmanship involved in creating these precast components. The BEBO arch itself is distinguished by its efficient load distribution characteristics, which allows for longer spans and reduced material usage compared to traditional bridge designs. Initially, the project commenced with detailed planning and engineering assessments to determine the optimal design tailored to Sarawak's unique geographical landscape. The production process involved cutting-edge machinery and experienced personnel who ensured that each arch element met stringent quality standards. The BEBO arch system is pre-stressed, which enhances its strength and performance, making it an ideal choice for the often challenging environmental conditions of the region. Transporting the precast elements to the installation site was another critical phase, given the size and weight of the arches. Special logistics planning ensured that each segment was safely delivered, with minimal disruption to local traffic and ecosystems. The team employed specialized vehicles and careful handling techniques, illustrating the commitment to quality and safety throughout the project. Upon arrival at the site, the installation of the BEBO arch became a focal point of the video. Skilled engineers and construction workers collaborated seamlessly, utilizing cranes and hoisting equipment to position the arches into place. The systematic approach adopted during installation ensured that the arches were aligned accurately and securely anchored, thus guaranteeing the structural integrity necessary for their intended purpose. The Rainer Square project in Seattle stands as a remarkable feat in modern construction and architectural design. As the city's newest addition to its skyline, the building will rise to an impressive height of 860 feet, making it the second tallest structure in Seattle. The ambitious project involved an intricate mat pour that not only symbolizes the foundation of the building, but also showcases the advanced engineering capabilities employed in today's construction practices. The mat pour, which is a significant step in the construction process, was executed with precision and efficiency. 8 concrete pumps worked tirelessly over a span of 16 hours to pour a staggering 10,872 yards of high-quality concrete. This process alone is an extraordinary coordination of resources and personnel, ensuring that the concrete is poured uniformly and without interruption to create a solid, stable foundation. The scale of the mat pour is impressive. It not only involved a vast amount of concrete, but also a substantial 1,500 tons of rebar, reinforcing the structure and ensuring its long-term durability against the U.S. Pacific Northwest's seismic activity. During the mat pour, 27,000 linear feet of finished concrete was laid, illustrating the remarkable logistical operation that took place. The successful completion of this phase marked a crucial milestone, paving the way for the upcoming construction stages. It highlighted the collaboration between skilled workers, engineers, and project managers who worked diligently under demanding conditions to meet the timeline. The completion of the Rainer Square project is anticipated around mid-2020, a timeline that reflects the complex nature of such a large-scale endeavor. The building is not just designed to provide office space, it also aims to enhance the urban environment of Seattle. Featuring modern aesthetics and eco-friendly technology, Rainer Square will contribute positively to the local economy and community. In a region known for its innovative spirit, the construction of Rainer Square underscores the intersection of engineering prowess and design ambition. The project embodies Seattle's growth and its commitment to evolving into a modern metropolis while maintaining its unique character. Moreover, as the skyline transforms with this new gem, Rainer Square will serve as a beacon of progress and a testament to the power of collaborative effort in the realm of construction. The mat pour represents more than just concrete and rebar. It symbolizes the promise of what lies ahead for Seattle and the continued evolution of urban architecture in the face of modern challenges and opportunities.